Okay, I think we can go ahead and get started here. I'm pleased to present today Sungsu Park, right there. Sungsu got his PhD in atmospheric sciences at the University of Washington in 2002. He came to NCAR as an ASP postdoc and then back to the University of Washington as a research associate from 2005 to 2008. And then returned to NCAR as a scientist 1 and then 2 in CGD. And starting in 2015, he's been a professor at Seoul National University in South Korea. His research interests include parameterization of moist turbulence, convection, and cloud processes in Earth system models, stratocumulus and cumulus dynamics, and cloud precipitation turbulence interactions. And there's the title, and I will mention that Chanwoo Song is also right here and will be speaking towards the end, but Sungsu will introduce him. So with that, I'll turn it over to you.
Thank you very much, Hugh, for introducing me. And this talk is about the work that I have been doing with my team in Korea during the last 9 years. The title is the Integrated Moist Physics Parameterization for the Earth System IMPrES with interprocess consistency. The Chanwoo Song, he's sitting there. He was my graduate student, and he finished his PhD last year. And he was one of the co-developers of this IMPrES model. And then Dr. Seeun Kim, she was here, but she left yesterday for Korea. And also a graduate student, Eujin Kwon, contributed to developing the IMPrES. And I want to express my thanks to Jimmy and Song-yu for hosting our visit to M-Cube. This is the content. I want to talk about the gradient issue, so-called scale-aware convection and the scale-adaptive convection scheme. And then briefly introduce the Unified Convection Scheme that I developed about 10 years ago when I was at NCAR. And then, since then, we also developed other physics parameterization. For example, we developed a stochastic convection scheme and elevated convection scheme. And then we developed a new cloud overlap parameterization for cumulus and stratus. And then Chanwoo Song, he developed a new dual PDF-based cloud macrophysics scheme. And Dr. Seeun Kim developed an advanced double moment cloud microphysics scheme with GraphL for cumulus and stratus based on the famous cloud microphysics scheme developed by Hugh. And then we refined various aerosol processes. And then there's a University of Washington moist turbulence scheme that I developed with Professor Chris Bretherton a long time ago. So all of these parameterizations, subordered parameterization, comprise a suite of advanced moist physics scheme, IMPrES. So at the end of our talk, we will briefly show our some work here during the last 1 month. Chanwoo Song has been working on implementing UNICON into the WRF model, and we will show some preliminary simulation result. So gradient issue, convection, it has been a long-standing issue, scale-aware versus scale-adaptive. I want to briefly explain what convection scheme does in the numerical models. Let's assume that this is one single grid box. Delta X is the size of a grid box. And we have convective updraft. It arises, and then it detrains its mass into the environment where the stable layer exists. And then if there is convective updraft mass flux, we have compensating substance motion. Okay. And sometimes if convective precipitation is generated, it can generate strong cold downdraft and then major scale organized flow like this. Okay. So all of these processes have different scales. For example, the observed upland radius is order of 1 kilometer. The order of these compensating substances can be as large as a couple of 100 kilometers. So convective detrainment may be larger than this updraft radius. And also major scale organized flow is larger than the size of updraft and convective detrainment usually. Now, convection scheme should parameterize all of these processes. if the size of grid box delta x is very large, such as 100 or 200 kilometers, then all of these processes are subgrid processes. So it can be parameterized in principle, even though it's not simple, okay? However, the problem happens if the size of grid box becomes very small, like this, denoted by dashed line. In this case, convection does not exist in the single grid box. For example, convective detrainment may exist in the nearby grid box. So compensating substance also exists in other grid boxes and also major scale flow. Now, then people have trouble in how to address this situation. That's just scale aware. So people have been working on developing so-called scale aware parameterization that can be used in this small grid box size. But there are lots of issues on that. I want to briefly talk about that. Okay, here is a fundamental assumption in all convection parameterization scheme. The goal is to compute the grid mean convective tendencies. But all the convection scheme compute this grid mean tendency using this equation. Here, A tilde is the fractional area of environment. A hat is the fractional area of updraft. So the sum of these two fractional area is 1. So convection scheme is computing grid mean tendency, assuming that the tendency is controlled by the environmental tendency, not the updraft tendency. So this equation is based on the assumption that the storage of the convective updraft area and the internal property is very small. And also the updraft fractional area is very small. Okay? Only on the condition that these three conditions are satisfied, we can use this equation to compute the grid mean convective tendencies. But the problem is that if the grid box size becomes very small, now this small fractional area assumption does not hold anymore. So we cannot use the conventional this equation. So let's look in more detail the equations used in the conventional convection scheme. This is vertical evolution of mass flux. We are familiar with this equation. This equation is based on the assumption that the updraft fractional area does not change with time. Vertical evolution of thermodynamic scalars also is based on the assumption that the updraft property does not change with time. And then finally, we compute the grid mean convective tendencies using this equation, as I explained. But we can split this equation into two parts. First part is the compensating substance part. Okay? Given the vertical profile of mean environmental scalars, by multiplying the updraft mass flux, we calculate compensating subsiding tendencies. And there's another term, this is convective detrainment tendencies. But here's the underlying, the hidden assumptions on this equation is that here, if you look at carefully, we are using updraft mass flux in this compensating substance terms. It implies that, okay, the compensating subsiding mass flux is existing in the same grid box, such that this environmental mass flux can be represented by this updraft mass flux. Okay? And also, this equation assumes that this detrained mass flux is existing inside the grid box. Okay? So these are the all hidden assumptions. All the convection schemes are using these three equations and also sometimes using this flux convergence form to compute the grid mean tendencies. The problem is that now, if the grid box size becomes small, then strictly speaking, these governing equations should be modified. However, all the people working on convection scheme do not modify these governing equations and simply allowing updraft fractional area approach to 1. Then that's wrong. Okay, let's talk in more detail. If the grid box size is similar to the size of updraft cumulus area, that's the situation of a so-called gray zone, I showed. Then this assumption that means that this compensating substance and detrainment exist in the grid box. These assumptions do not hold anymore. This means that we should partition this compensating subsiding mass flux and detrained mass flux to nearby grid boxes with appropriate modifications of this term and this term. This approach is very, very complicated and uncertain because we don't know the spatial scales of this compensating substance and determine the mass flux. And also, most problematic part is the major scale organized flow. Okay. It also violated the steady state plume approximation, this assumption. Okay. And also, in this case, this grid mean tendency cannot be represented by this environment mean tendency anymore. It should be represented by the object tendency because object fractional area is much larger, it's approaching to 1. So consequently, in the gradient of a small grid box size, we should use a prognostic plume model with an appropriate partitioning of the compensating substance and determine the mass flux and major scale organized flow to the nearby grid boxes with the necessary modifications of these 4 carbon equations. This is a so-called scale-aware convective parameterization. But the problem is that so-called scale, there are a couple of scale-aware convection scheme. They don't use modified equations. Okay, they don't care about whether this major scale flow or compensating substance exists in the same grid box or in the nearby grid boxes. Now, another way to avoid these complexities is to transform this objective size into much smaller size. I'm calling this one a scale transformation, such that grid box is much smaller than this transformed plume radius. So the objective fractional area is very smaller than 1, and also grid mean property is largely determined by environmental properties. Here our head is the relative suborbital plume, not the real plume. So if we follow this approach, then we can use this conventional governing equation as it is without changing any atoms. Okay? So this transform allows us to use all the above governing equations without any modification. I am calling this approach the scale adaptive convection parameterization because in this approach, the plume radius is not the radius of a real plume. It's the radius of some kind of relative suborbital plume. So here we have 2 approaches. First, the scale-aware model. It assumes that any direct atmospheric flows associated with observed convection, a convective updraft, downdraft, detrimmed, and the compensating substance, major scale flow are simulated by the convection scheme. Okay? Convection scheme first simulate everything related to the observed convection. Okay? And then the advection scheme simulated the other non-convective 3-dimensional grid mean flows. Okay? And that the convection scheme in this case is an intergrid model. That means that the mass flux, sum of all the mass flux is not 0. Compensating substance is existing in the nearby grid boxes. Okay? On the other hand, the scale adaptive model use this concept. So regardless of the origins, any 3-dimensional grid mean flows are simulated by the advection scheme. So advection scheme first go, and then the convection scheme simulates relative with respect to the grid mean flow, suborbital flow by non-local asymmetric turbulent eddies. So in this case, the convection scheme simulates not real plume, but relative plume with respect to the grid mean. So the convection scheme in this case is a single column model. The sum of mass flux in this case is exactly 1, so we can use the conventional governing equations. So scale-aware model first treat convection and then treat advection. Scale adaptive scheme is first handle the advection scheme, and then convection scheme should simulate the remaining relative suborbital transport. I want to explain in a more clear way using this diagram. Let's imagine this situation. This is nature. G is the size of grid box. Let's assume that the size of a grid box is much larger than object plume. This is the radius of object plume. This is the radius of compensating substance. The scale of this compensating substance is 100 kilometers, and radius is just 1 kilometer, for example. So let's assume that the size of a grid box is very large, such that the object and compensating substance mass flux is existing in the same grid box. Okay? This is the real situation. This is the situation in the normal general circulation model. Now, if we have a scale-aware scheme, as I said, then convection scheme first simulate this observed convection, every observed convection as it is. So convection scheme simulates everything, observed convection-related phenomena. Then advection scheme simulates the other three-dimensional flow not related to the observed convection. So in this case, I'm assuming that there is no large-scale grid mean vertical flow. So grid mean of vertical flow by advection scheme is 0. Let's see, what does a scale additive scheme do? Scale additive scheme first do the advection scheme first do the grid mean flow. So in this case, there is no grid mean vertical flow, so advection scheme does not do anything. And then the convection scheme does the remaining relative vertical transport with respect to the grid mean flow. But in this case, because there is no grid mean vertical flow, this relative subordinate convection scheme is doing the same as the one as the scale-aware scheme. So when the grid box size is very large, there is no difference between scale-aware and scale-additive convection parameterization. They are identical. Okay. Now let's go to this situation of this so-called gradient issue. Okay. There, in the case, the size of grid box is much smaller than the size of compensating substance. Okay. And then in some cases, it can be comparable to the size of a convective updraft plume. Okay. Let's imagine this situation. This is real convective updraft, and this is, we have a compensating substance. Really, in a real situation, this compensating substance is existing in a much larger domain. Now, let's see what does the scale-aware convection scheme do, okay? In this case, as I said, the scale-aware convection scheme should simulate everything related to the observed convection. Okay. It should simulate observed convective updraft and observed compensating substance. And then the advection scheme does the remaining non-convective three-dimensional grid flow. And in this case, I'm assuming that there is no vertical grid in vertical velocity. So advection scheme does not do anything. Okay. Then what does the scale additive scheme do? This is the key. In case of scale additive parameterization, the grid mean flow first do their role. So in this case, the grid mean flow driven by convection is not 0. Okay? It will have some kind of positive vertical velocity. So advection scheme will perform some of the observed vertical transport by the observed convection. And then scale additive convection scheme does the remaining relative subgrid vertical transport. Okay, so if we subtract this from this one, the color and the size of this objective fractional area should be slightly different from one. But here is a trick. So after doing this average transport by the grid advection scheme, we should do so-called scale transformation. This size of objective fractional area is transformed into the much smaller relative plume size, such that the fundamental assumption in the whole convection scheme that objective fractional area is very small, such that we can use a diagnostic plume model. Those kind of assumptions should be used. In order to do that, we should perform a scale transformation from this large object to the small object plume size. Now, UNICON is developed based on this scale additive concept, okay, not a scale aware concept. This table summarizes the difference of scale aware and scale additive convection scheme. Okay, so parameterization target of convection scheme. Scale aware convection scheme, the target is observed convection. But scale additive scheme, the target is relative subgrid convection with respect to the real grid mean flow. Now, conceptual order of convection and advection scheme. Scale-aware scheme, convection scheme first to go, and then advection scheme. Scale additive scheme, we first do advection and then convection. Now, let's compare the size of grid box and the compensating substance. If the grid box size is comparable to the compensating substance, that's the case of a very large grid box. And also this is the situation of small grid box, so-called gradient. Okay? In these two size limit, let's see how these two schemes treat various properties. Now, which scheme simulate the observed convection? In case of a scale-aware scheme, regardless of the size of grid box, the convection scheme should simulate the observed convection. However, in case of a scale-additive scheme, If the grid box size is very large, the observed convection is simulated by a convection scheme. But if the size becomes very small, the observed convection is simulated by the advection scheme. Okay. Now, in-grid compensating substance and upwelling. Now, if the grid box size is very large, yes, scale-aware scheme contains grid compensating substance within the same grid box. However, if the grid box size becomes small, the compensating substance does not exist in the same grid box. However, in case of a scale-additive scheme, always compensating substances exist in the same grid box. In-grid convective detrainment, yes, same as the compensating substance. In-grid mesoscale organized flow, same. Okay. Quasi-equivalent assumption within grid box, in this case it's valid, but in this case it's not valid because in reality this equilibrium is achieved by compensating substance. So we cannot assume quasi-equilibrium in this limit. Then obturator fractional area, yeah, in this case very small, lower than 1, it's good. But if the grid box size becomes small, it approaches to 1. But in case of scale additive, it's always smaller than 1, much smaller than 1. Diagnostic or prognostic plume, yeah. In this case, diagnostic, but if the grid box size becomes small, it should be prognostic. But the problem is that all the convection schemes are using diagnostic approach, even in this limit. Okay, that's conceptually not correct. Scale additive scheme is always diagnostic. And then does the grid mean contain incumulus properties? No. And in this case, yes, because observed size is very large. Okay, but in this case, no. Horizontal advection of convective plume? No. Yes, no. And then column integrated quantity is conserved. It's conserved if the grid box size is very large, but if not, then it's not conserved because we have compensating substance in the nearby grid box. Scale additive scheme is always conserved. Okay. So people are stuck in this gradient issue because they think that the convection scheme should simulate the observed convection scheme, observed convection as it is, the scale-aware concept. With this concept, the treatment of convection in the small and large grid box size should be completely different. Yeah. But however, if we switch to the scale-adaptive idea, we don't need to use separate equations. We can use all the conventional equations. Now, perhaps are conceptually easy. Oh, subordinate convection simulates the observed convection as it is. Cons, practically, it's almost impossible. Very, very hard. Okay. Scale additive scheme, conceptually hard. The concept of relative plume is somewhat hard to understand. However, practically, it's very easy. Okay. We can use the conventional equation as it is. Now, so people use this equation that if the grid box size becomes very small, such that observed fraction area increases, they change those equations, but that is not correct. If they want to use really these approaches with a small grid box size, they should not use the diagnostic plume model. They should use the prognostic plume model. But the problem is that it's not. And then we can apply the same argument in the temporal domain as well as the grid spatial domain. Okay. Now, two approaches. Let's assume that we are hiking. We can hike following the terrain. It's really hard, but it's realistic. I'm calling that the hiking is a scale-aware hike. Okay, just to follow the real terrain as it is. Okay, that's the best ideal approach, but it's really hard. Another approach is to use the cable car. Okay, just realize, invent some idealistic situations, and they make the problem much more simpler. Okay, which path is more safe, or economic and rewarding? It's a choice of problems. Okay, any method is okay, but we should use some conceptually consistent approaches. Now, I want to switch to the next topic, the scale unified convection scheme. I developed UNICON about 10 years ago when I was at NCA CGD division. And then after developing the UNICON, I left NCA. 10 years later, I heard that not much so progress was done in the convection parameterization. So I came back here. And this is the first line of abstract of my paper. So the author developed a unified convection scheme that parameterizes relative with respect to the grid mean vertical flow, suborbital vertical flow by non-local asymmetric turbulent eddies. So it's not a real convection scheme, it's relative polar model, okay? So it does not suffer from this gradient issue. What is UNICON? This is conventional view how we treat the suborbital vertical transport. Within PBL, we have local transport, non-local transport treated by PBL scheme. And above the PBL, we have a separate shallow and deep convection. And sometimes we have a separate free tropospheric moisture transport term, similarly in all the weather forecasting and GC models. Now, in the UNICON, the framework is changed. So regardless of the vertical layers, all the local transport is simulated by a moist turbulence scheme, University of Washington moist turbulent scheme. And the remaining non-local transport, relative non-local transport, is simulated by UNICON. For example, we have a convective updraft here, then we have a compensating substance motion. We have convective downdraft here, and we have compensating upwelling motion. And sometimes precipitation is generated, and it evaporates, and it can generate this cold air, and the cold pool, and it will generate this suborbital measure scale organized flow. So UNICON is designed to simulate this convective updraft and downdraft and measure scale organized flow driven by the evaporation or precipitation. Okay. So it simulates a convective updraft, downdraft, measure scale organized flow. As I said, it simulates relative suborbital vertical transport. It's a scale adaptive parameterization. It consists of lots of processes. It simulates all dry, moist, first free, and shallow deep convection within the single framework in a seamless, consistent, and unified way. It does not have any separate treatment for shallow and deep convection. Everything is treated in a smooth way. Okay? So this shows the vertical profile of potential temperature and the vertical wind shear. Then UNICON launches plume from the surface. It goes up, and it is saturated at LCL. And it may not go over LFC. So this plume should come back. Okay, this convection is so-called first convection. But none of the convection scheme is simulating a first convection. Okay, sometimes this convection can grow above a level of free convection, becomes a free convection, moist free convection. But all the convection scheme simulating this one, but not the first convection. But UNICON simulate the first convection. And then during the entrainment process, evaporative cooling occurs, and then precipitation, if the precipitation is evaporated within the downdraft, it can generate this downdraft that can penetrate down into the PBL, and it can generate the major scale organized flow. Okay. In this way, UNICON simulate dry, moist convection, and first free convection, and the shallow and deep convection in a single, in a consistent and simplified way. Okay. I want to briefly explain how the UNICON treat major scale organized flow. Let's assume that this is one grid box in PBL top height. We know that the convective precipitation falls into some localized spot. Then it can be evaporated within the PBL, and the cooling occurs, that's the cold pool. Then we have some available potential energy due to the horizontal temperature gradient. Then it can generate a major scale organized flow. And then convective updraft grows here, so it can force convective updraft. So if there is a strong cold pool generated by evaporation or precipitation, it can strengthen convective updraft plume. But that's the way how UNICON simulate cold pool. This same diagram here. So if we have cold pool generated by convective downdraft and evaporation of precipitation, we are assuming that generates major scale flow. It changes the updraft properties and vertical velocity and radius and fractional area of convective updraft plume at the surface. Okay? There are complicated equations to compute all of these processes. This shows the perturbation of updraft properties by suborbital cold pool generated by UNICON. This is perturbation of potential temperature at the surface by cold pool. So here you can see that there is about 0.56 Kelvin perturbation by cold pool simulated by UNICON. And this is perturbation of observed vertical velocity. Here in this case, 0.3 or 35 meter per second in the deep convection region. So if there is a cold pool that enhances convective observed plumes, so it simulates more deep convection-like phenomena. If there is no cold pool, the convection will be more like a shallow convection. Okay? This is the way how UNICON simulates both the shallow and deep convection in a smooth way without any on and off switches. Okay? So UNICON consists of diagnostic subordinate convective updraft and diagnostic subordinate convective downdraft. The problem is that those two plumes are diagnostic in all the convection scheme. So we don't have any temporal on memory. In order to address that issue, we developed the cold pool parameterization, and then the property of cold pool is treated in a prognostic way. Okay? So then prognostic treatment of a subordinate cold pool and measure scale flow allow UNICON to carry the convective plume memory across the model time step. So by using this prognostic treatment, so you can simulate, for example, dynamic cycle of precipitation in a more realistic way. It has convective updraft and downdraft measure scale organized flow. Consists, and then, as I said, convection and advection, they are not separate properties. They should simulate the real convection in a combined way. The convection scheme is not simulating the real convection, but the combination of convection and advection scheme should simulate the real convection. Okay? That's the scale adaptive concept. Okay, I want to explain this one. Then we know that all the convection schemes, if it is really scale adaptive or aware, should satisfy the conditions. The first condition is that if the grid box size becomes small, the grid mean convective tendency approaches to zero. So in a small grid box size, then we turn off a convection scheme. So this state that requirement. However, there's one additional important condition. If the grid box size becomes small, the spatial temporal variability of grid mean convective tendency should, with respect to each mean grid mean tendency, should increase. Okay? Even though the grid mean convective tendency becomes very weak with a small grid box, then the variability of this convective tendency should increase because in nature, the convective updraft plume have a stochastic property. So for a given same environmental condition, the property of convective updraft can differ because it has a stochastic nature. So because of that, its variability should increase if the grid box size becomes small. So UNICON achieved this first condition because its entrainment rate is parameterized as a function, inverse function of plume radius. So if the grid box size becomes very small, plume radius approaches to zero. So entrainment rate goes to infinite, such that convection just naturally diminishes. So grid mean convective tendencies go to zero. And the second requirement is more complicated. UNICON satisfied the second condition by launching a few beam plumes and one stochastic plume with different vertical velocity, temperature, moisture, and plume radius in number concentration. This imposes stochastic perturbation on the mass flux of observed mass flux and grid mean convective tendencies with smaller number concentration in a small grid box. Consequently, as the grid box size becomes small, the variability of grid mean convective tendency increases. I will show one on the figure. Okay. So this is the unified convection scheme, and probably I don't have enough time, so I just very quickly introduce the IMPrES. UNICON is a convection scheme. However, our goal was to develop a suite of comprehensive physics parameterization, not only convection, but also macrophysics, microphysics, and aerosol and moist turbulent scheme. So we work on those stuff. From Chem 5, we developed SAM0 UNICON by adding UNICON into the Chem 5. And from SAM0 UNICON to IMPrES, we added a lot of many other components, advanced UNICON, stochastic convection, elevated convection, integrated vertical cloud overlap macrophysics scheme, and double moment cloud microphysics scheme with the graphel. And then we implemented it into cumulus and stratus. and then refined various aerosol and radiation processes. And this is a diagram how the IMPrES perform various suborbital physical processes. I want to switch this one. And then the bottom line is that with double moment cloud and microphysics, both in the convection and large scale cloud, we can simulate these aerosol cloud interactions, both for the stratiform and the convective precipitation. Okay. Now I want to, maybe I don't have enough time, but I want to show a couple few slides. This is a simulation result with our most recent GCM IMPrES compared with CAM5 with UNICON. For 10 climatological variables, we compare the root mean squared errors and bias. In terms of root mean squared error, this model improved by 10%, and bias, it improved 25%. Okay. Then I want to switch to detailed explanation on the stochastic UNICON and elevated convection. Originally, UNICON launched plume from the surface. However, we realized that it cannot simulate the nocturnal precipitation over the Central United in the summertime. So we additionally added so-called elevated convection. In IMPrES now, UNICON also launches the elevated convection from the level of maximum gradient mean moisture static energy, as well as at the surface. The result is here. This is a southern great plain cycle of precipitation for the nocturnal, afternoon, and clear in all cases. This is afternoon precipitation case. This is local time. Black is the observation, afternoon precipitation maxima. The original UNICON denoted by blue already were simulated afternoon precipitation maxima. But if you look at nocturnal precipitation over the United States in summer, the observation shows nocturnal precipitation, but the original UNICON simulated the afternoon maxima. But with the elevated convection, it simulates well this nocturnal precipitation maxima. And this is a total simulation cases. Again, with the elevated convection, it simulated both this nocturnal and the afternoon precipitation maxima well. Cloud overlap, I want to switch this one, and then switch macrophysics. And then I want to switch this, I want to explain double moment cloud microphysics scheme. So based on the Morrison-Gellman microphysics scheme that Hugh developed, we added graphite processes, various graphite processes, and we refined liquid auto conversion and accretion rate. Instead of using empirical formulation, we used more physical stochastic parameterization. And then there are various source processes and sync processes for the graphite process. And then we, after developing this advanced scheme, we implemented this scheme into both the convection and large-scale precipitation model. And then implementation of double moment cumulus microphysics in UNICON was really complicated. It took about 4 to 5 years to do that. And Dr. Seung Kim finished this work. We have aerosol activation at the cumulus base, and then auto-conversion accretion, and then various other processes. And also, we also have a secondary aerosol activation. The entrained air can be activated here, okay? So we have many other kind of microphysical processes in the updraft and the downdraft and the environment. So we added all of these processes both into the convection and large-scale precipitation processes. Yeah. This is one example of this double moment cumulus microphysics scheme. The size of a cloud liquid droplet within cumulus updraft and ice crystal denoted by this color shading. Originally, the size was specified, but with the double moment cumulus microphysics scheme, we have some varying droplet size within the cumulus. Okay? And then we refined the various aerosol treatment. Then I want to show one final figure and switch to the China's talk. What we did was that, okay, now we have new model that can simulate aerosol cloud precipitation interaction both in the cumulus and stratus. So what we did was that, okay, within the convection scheme, we arbitrarily enhanced the secondary aerosol activation, and then we checked what happens. People said that, if we have more aerosol within the cumulus, then we may have less precipitation, so we may have more cloud liquid droplet that can be converted into ice crystal. So freezing heating may increase, so it can deepen convection. However, the Hugh argued that is not correct. Now we can test those hypotheses with our model. So with more aerosol activation within convection, we were very surprised by this result. Okay, cumulus height increases in many areas, consistent with conventional invigoration hypothesis. But surprisingly, in some areas, especially over Africa, the cumulus scale height decreases. So something is going on that cannot be explained by a simple aerosol invigoration effect. So we are working on analyzing this result. Now, in the last 5 minutes, I want to switch to the last topic. UNICON, we implemented into WRF. This work is done by Dr. Chan Woo-sung and Siyoon Kim. And I want to express my thanks to Dr. Sung Hong and Jimmy Dudia for their help in this work. And I want to mention that UNICON does non-local transport within the PBL. It means that such that UNICON should be combined with a PBL scheme without a non-local transport term within the PBL. And that scheme was eudaimoist turbulent scheme that I developed with Chris. So we will show some preliminary simulation result with UNICON and eudaimoist turbulent scheme implemented in the WRF model. Okay, so, yeah.
Hi, my name is Chan Woo-sung, and during the last few weeks, we implemented UNICON into WRF. And we run 2 tropical cyclone cases. One is Hurricane Mikhail, and the other is Typhoon Jebi. These are the simulation settings. We use 12 kilometers of delta X and 45 vertical layers and 60 seconds of delta T. We conducted 3 types of simulation. First, we run the original WRF using the M-cube setting. The physics suite named Tropical for the M-cube setting has convection scheme of UTD-key and YSU PBL scheme. Second, we run UW-MT model, which use the University of Washington moist turbulence scheme instead of YSU PBL. Then we run UNICON with UW-MT, which replace the UTD-key scheme and YSU PBL scheme. These figures show Hurricane Mikhail's track and minimum sea level pressure. Black line indicates the IB tracks observation. Blue, orange, and red line indicates the simulation result obtained from the original UW-MT and UNICON simulations. This figure shows that tropical cyclone tracks obtained from the original and UW-MT are quite similar. However, UNICON simulated different track to them. Note that the RMSE scores of UNICON is better than these two. Right figure shows the time series of minimum sea level pressure. In the earlier stage of the tropical cyclones, UNICON, the red line, well follows the observation. The other 2 simulations underestimate the observed intensity of tropical cyclones. However, after the 3 days of simulation, UNICON simulates UW-MT and the original WRF performs better than the UNICON. This figure shows track and minimum sea level pressure of Typhoon Jebi obtained from the observation, original WRF, and UNICON. Unfortunately, UW-MT simulation is crashed for this Jebi case. UNICON simulated more reasonable tracks of Typhoon Jebi. RMSE score decreased from 2.88 to 2.49. The minimum sea level pressure of UNICON is stronger than the original WRF. The bias of the original WRF was 37.3, and UNICON significantly decreased the positive bias of TC intensity. This figure shows the minimum sea level pressure of Typhoon Jebi obtained from the observation and original WRF using the 12 kilometer delta X, original WRF with 6 kilometer, UNICON with 12 and 6 kilometer. First, both the original WRF and UNICON simulated stronger tropical cyclones with finer resolution. However, UNICON with 12 kilometer simulated stronger cyclones compared to the original WRF using the 6 kilometers. Finally, UNICON with 6 kilometers simulated better time series of tropical cyclone intensities compared to the other three models. So I will gonna give you to Professor Sungsu for the summary.
Okay, thank you very much, Sana. Yeah, this is the summary. So UNICON consists of updraft, downdraft, measure scale flow. It simulates all dry, moist, force-free, and shallow-depth convection. And then UNICON is a scale-adaptive scheme, not the scale-aware scheme. It simulates relative subgrid plume with respect to the gradient flow. It bypasses the gradient issue by parameterizing the updraft plume radius and the plume number concentration as an increasing function of the grid box size. People are saying that, they have developed a scale-aware convective parameterization, and then by allowing the updraft fractional area to 1. But that approach is not correct. If they want to use this approach, they should use a prognostic plume model. But all the convection schemes are using diagnostic plume model. So it's not, it has some problem. And we developed IMPrES by adding various new component. And then IMPrES can simulate aerosol indirect effect. Now this is the most important part. So I am working on implementing and testing UNICON in various research institutes. First, I work with NOAA, with Dr. Bao. Dr. Bao is here, in implementing UNICON into the NOAA UFS model. And also, I'm visiting here to work on implementing UNICON into the WRF model with Jimmy. And also, we are implementing our scheme, and we have implemented our scheme into the KMA unified model and the KIAP scheme model. And also, the UK Met Office, they have been developing a new convection scheme, so-called ConMorph, based on the conceptual ideas suggested by UNICON, and I'm collaborating with them. And I heard that NCA is in the transitional stage from WRF into the MPAS. So even though I'm working with WRF, then I'm not sure if there is a chance I may test this model, UNICON and IMPrES, in the MPAS framework. And finally, with IMPrES, we have a plan to participate in the CMAP 7 project. Okay, that's all of my presentation. Thank you very much.
Thank you. Time for questions?
Yeah.
Yeah, that's very interesting. But since we are in the mesoscale division, I'm curious whether you try to do something which would be very simple test, the way I think about it. Let's talk about organized convection. Let's take a squall line and try to simulate it with grids from whatever, 20 kilometers to convection allowing 5 kilometers or 2 kilometers. Have you tried something like that? That would be really a very good, to me, very convincing test that you can do organized convection with UNICON.
Right. Thank you very much.
This?
Yeah, thank you very much for that. Yeah, that's very good comment. We have a plan to do that. We visited here in just for 1 month. So we have just finished implementing the UNICON into the WRF, maybe the day before yesterday. So
just keep my comment in mind.
Yeah, I will definitely do that by changing the horizontal resolution from 12 or 20 kilometers down to 1 kilometer, whatever. We want to test whether this model really simulates this squall line cases. Yeah, that's our very next test subject. Thank you. Yeah.
Thank you for your presentation. I think you mentioned that the scale adaptive scheme is turning itself off as you decrease the grid spacing.
Right.
So at what grid spacing would the scheme be essentially off? What is it 1 kilometer? Or is it actually going down to 500 meters, 250 meters?
We don't know. We actually should do the real test, okay? Here, so as the grid box size becomes zero small, the grid mean convective tendency should approach to zero, okay? That's the scale adaptive or scale or whatever. Now, in our model, the entrainment rate, fluid entrainment rate is parameterized from this so-called mixing rate multiplied by some factor. This mixing rate is parameterized as a function of this plume radius, okay? Now this is the radius of relative plume, okay? Not real plume. Now this condition should be satisfied. Pi multiplied by the size of relative plume should be smaller than the grid box size and multiplied by 0.1, okay? So let's assume that A max is 0.1. If we use a small grid box size, then plume radius should decrease, okay? As plume radius decreased, this plume entrainment rate should increase, okay? Everything is treated in a continuous way, okay? There's no on and off switches. So we really don't know. Let's assume that we ran the model at the 1 kilometer resolution. Then we know that this plume radius should be very small, okay? In this situation, we know that the entrainment rate will become very large, so convection will become small, but it will not go to zero, okay?
Right.
We should actually run the simulation. Yeah.
Okay, thank you.
Yep.
Yes, I just want to make a quick comment following up with the previous question.
Uh-huh.
I think at what resolution the scheme is effectively turned off
Uh-huh.
is dependent on the characteristics of dynamic core.
I completely agree with you. Yeah. Yeah, because I heard that the finite volume dynamic core has more some dissipation properties than damping properties than the IMPrES, for example. Okay, as I mentioned, the observed convection is simulated by the combination of advection and convection scheme, not by a single convection scheme. Okay, so if we want to really simulate the observed convection realistic way, the combined advection and convection schemes should be well developed. If advection scheme is more dissipative, then the convection scheme should be less dissipative in order to simulate the observed convection as a combination. So as you said, the properties of the convection should be dependent on the dynamic core that we are using. It should be tuned against the dynamic core, okay? Yeah.
Okay, we have a question on the Slido from Kevin Rader. In the simulations of typhoons, it looked like the initial conditions did not represent the storm very well, and that mismatch was carried through the simulation. Do you have plans to generate better initial conditions for these tests?
Yeah, that's a good question. Maybe Chan may answer, and also I will give some answer. This was a very initial preliminary result. We just finished it today morning, so we did not have enough time to do more in-depth test. Yeah.
Thank you for the question. And for this question, as Sungsu said, this is very preliminary test result using the quite coarse resolution for tropical cyclones. I think we will plan to do some kind of boxing for the tropical cyclones to generate better initial conditions for the tropical cyclones. Then the tropical cyclones could start with quite intense stage and could get better time series of tropical cyclone time series.
Okay. Yeah. Did we answer to your question, Kevin?
Did you want to add anything to that, or we can move on?
I think
to the next question.
that's it. Yeah.
There's any more?
We want to do some focusing, but we want to get some comment if you have any suggestion and ideas on how to do more realistic tropical cyclone simulation. Yeah.
Well, sorry to be a little bit obnoxious. This result about this convection invigoration, as we used to call it, the effect of aerosols on convection. You showed just one snapshot. It's kind of amazing that it's completely different over land than over the ocean. So I'm curious whether that has to do really with aerosols or with just convection over land versus over ocean. And of course, as you know, Hugh and myself have very strong opinion about this kind of bogus effect that got us into discussions which really kind of goes and goes. And I think we know what's going on, and some people keep insisting that, this is real, this is invigoration. No, exactly. That it's really kind of strange that it's...
It's like over Central Africa.
Well, so...
Amazon is still going positive.
It's not everywhere. So Amazon is kind of neutral, but Africa is definitely on the negative side. So it's kind of curious. Anyway, I dig more into that. And of course, we are convection, people. So parameterized convection and especially aerosols in it is what I call parameterization squared problem. Parameterized microphysics and parameterized convection. So it's parameterization squared problem.
Right.
More difficult. But it's a good test. And we have simulations that I think show what's going on in the real world compared to parameterized world.
That's a very good comment. And we were surprised by this result. It may support your some argument or whatever. So, but one of my graduate students, Eugene Kwon, has been doing very in-depth analysis, and he found some plausible explanations on why this happens, and we are working on that. And then what I want to briefly point out is that so Eugene Kwon collected lots of observations, some data set, examining the impact of aerosol on the convection strengths, and what he found was that so he found some observation studies saying that the aerosol in the Africa may weaken the convection, but aerosol in other regions may strengthen the convection. So
when you're looking at laptop height, laptop height is not a measure of strength of convection.
I see.
It can change, for very different reasons.
I see. Then do you have any other good measure or some?
Steve Massey did some analysis on that. I can send you the Remember Steve Massey analysis? Laptop height analysis and link to.
Great.
500 meters is not a very big signal comparing to what models. Especially climate models.
But these results are statistically significant. We did some statistical tests, but the paper from them will be very good for us. Thank you.
All right. Let's thank the speaker once more.
Thank you.